Hi everyone, this is Matt Touchot with Intro Stats, and today we're looking at a problem from my book, Intro to Statistics for Community College Students. This is section 4B, as in boy, number 30. Alright, so here it is. This is a problem where we're going to be using randomized simulation this time to calculate our p-value. We're going to be using stat key, so we'll do this. Let's read the question. It says, under the Anova for difference in means menu and stat key, click on the button on the top left. It says sandwich ants. We are studying the number of ants that are drawn to different kinds of food. In this data, we are looking for the mean average number of ants that come in 3 different types of sandwiches left out to spoil. Use a 5% significance level to test the claim that the number of ants is not related to the type of sandwich. Okay, so we've said in Anova that the null hypothesis will be the means are equal to each other, and then the alternative will be at least one of the means is not equal to each other. If the population means are equal, that means it doesn't matter what sandwich is left out. We get the same average number of ants, and that would indicate not related. If the mean averages are significantly different, then it seems like it does matter what sandwich is left out, and we're thinking that the sandwich is related to the number of ants. Okay, so let's take a look at this. So if we go to stat key, again, it's on lock5stat.com. Just click on stat key, and we're looking for Anova difference in means. It's kind of in the bottom right corner. So we're doing an Anova simulation, basically. All right, let's see. Oh, the sandwich ants looks like it's the first one up. So this actually is the data. Here's the data. We have the sample mean number of ants for the various sandwiches left out. And we can see the F test statistic is right here, 5.627. We can look at these standard deviations real quick, 9.3, 14.6, 10.8, and 13.4. None of them are more than twice as big as any other. So it is going to pass that assumption of that the standard deviations are relatively close and the variances are relatively close. If you want to see the Anova table, we can see right here that the 780.5 is the variance between the groups, and right here where it says MS error, that's the variance within the group. So again, the variance between is about 5.6 times higher than the variance within. So this is just kind of how those numbers were calculated. Okay, notice the null hypothesis, mu1 equals mu2 equals mu3. Remember, that would mean not related. That means it doesn't matter what sandwich is left out, we're getting about the same average number of ants. If at least one of these is not equal, then it would indicate related. Okay, so again, we're looking at type of sandwich is our categorical variable, number of ants is our quantitative variable, and we're trying to see if those two things are related or not. The problem said that the claim is that they're not related. Okay, so that would be the null hypothesis. All right, so let's go ahead and generate a few thousand. Now we're in a multiple population now, so we're going to be using the actual test statistics. So what the computer's going to do is it's going to generate random samples under the premise that the mean averages are equal, and then it's going to calculate thousands of F test statistics. So thousands of F test statistics over and over and over again. So let's do that. Click 1,000 samples a bunch of times. We can see right away that the F distribution looks very skewed right. Yeah, so there's our F distribution, looks very skewed right. And again, these where it says randomized sample, these are just the information on each of these F test statistics. Now the problem said that they want us to use a 5% significance level. Remember, Anova is a right-tailed test. So I'm going to click right tail, and I'm going to put 0.05 in the right tail. So in that top percentage right there, change it to 0.05, and this is where our tails start. So the computer thinks that, or the simulation thinks that the F test statistic needs to be 3.593 or higher to be considered significant. So does our real original sample F test statistic fall in the tail? Well, I think we can see it does, right? 5.627 is kind of in here, right? Which is definitely in the tail. Now again, remember, this is randomized simulation. All of us will get the same original sample F test statistic, but this critical value right here, 3.593, there will be slight variations when you do it versus my simulation. Remember, my random samples are slightly different than your random samples, so my critical value from this simulation will be a little different than yours, but I bet we're pretty close. So main thing we see is that the original sample F test statistic does fall in the tail. So what does that tell me? Well, what all test statistics tell you, right? If the test statistic falls in the tail, that means the sample data does significantly disagree with the null hypothesis. That also means, by the way, that the variance between the groups is actually significantly higher than the variance within the groups. All right, now what about my p-value? Now my p-value, this is not a p-value, this is the significance level. Remember, to get the p-value, we need the probability of getting this original random sample here, this original sample, the real one. So what you want to do is put this 5.627 in this bottom box right here. So in the bottom box, I'm going to put in the actual F test statistic from the original data. And then right above it will be the p-value. So the probability, if the null is true, the probability of getting the sample data, this sample F test statistic, or more extreme, by sampling variability, this is all sampling variability, is this number. This is the p-value. Again, you will have slight variations in p-value since your simulation is not the same as mine. Your random samples, when you do this, are going to be slightly different than this simulation I'm doing right here. So you might get something slightly different than what I got. I got 0.013 or about 1.3%. And that is lower than our 5% significance level. So it's unlikely to be sampling variability, and we can reject the null hypothesis. Now, if you remember, the null hypothesis actually was the claim, because I said the claim is that they're not related. So this is telling me that since we rejected the null hypothesis, and the null hypothesis was the claim, we're actually rejecting the claim. So there is significant evidence to reject the claim that the sandwich is not related to the number of ants that come. In fact, this is more indicating that the sample is related to the number of ants that come. Okay? All right. So as long as this was random sample data and independent, it would pass the assumption for a randomized simulation, so we're probably okay. Even if the sample sizes are very small. All right. So this is Mat 2 show and intro stats, and again, this was section 4B, number 30. All right, see you next time.